Hello there. This is a walkthrough of the A-level fields topic capacitance, mainly based on the content of the AQA course. So this follows directly on from the electric fields topic, and if you've managed to watch the electric fields video, that would be good. So let's get into it. So a capacitor is a device for storing electric charge. There's the symbol for a standard capacitor. Most capacitors consist of two parallel conductors separated by a thin insulator or air. Pre-2015 on the AQA course, there were questions were just about air as the dielectric, but since 2015 they reinstated dielectrics, brought that back into the course so they could ask more questions. Now there's a little bit of language issues here we should address. So students should be aware of uncertainties, and so the word tolerance is often used for capacitors and other electrical devices. So tolerance is the same as the uncertainty, really, okay? Just to be aware of that word, but often it creeps into exam questions. So capacitors could have a tolerance of up to 20%, a little cheap component. So it might not be exactly what you think it is in terms of capacitance. And they're only guaranteed to within, that 20%, say, of the nominal value. So that's another word. So the nominal value is the value that is written on the capacitor, or the value that they're allegedly supposed to be. Okay, so the nominal value and tolerance, they are terms that students should be familiar with. And storing charge is their purpose. Used in loads of different gadgets. Form those capacitors together with diodes and transistors form the basis of electronics, essentially. Uses, a huge number of uses: regulating power supplies, timing circuits, tuning. So in courses where there's, I know in the WJC courses, an AC theory section, and tuning circuits, could be part of that. Backup power supplies as well. Really important devices. So two parallel plates typically, although there was a question fairly recently where they were talking about a variable capacitor, which is more of a fan of plates, a bit of a different arrangement. So basically the area of the plates has changed. So that's something to be aware of. So they can differ from just two parallel plates. Two conducting plates separated by a gap, or with a dielectric or air or a vacuum between those plates. So the shape of the plates is generally square in a lot of questions, could be circular as well. And when a capacitor is connected to a power source, you get build-up of positive and negative charges on the plates. They build up on opposite plates, and they create a uniform electric field between the plates. The first equation, really the most important equation, really is the capacitance equations. Capacitance is equal to charge divided by voltage. And in terms of units, the unit of the capacitance is the farad, named after Michael Faraday. It's a huge unit, so it's going to be, you're not going to see many just farads appearing. We have a 50 farad supercapacitor in school, but generally capacitors are going to be microfarads. Sometimes they're written as thousands of microfarads, for instance. Could be nanofarads or picofarads. So those prefixes need to be really well known by students. So sometimes I've seen questions in exam papers where they say, what does 2,200 microcoulombs mean? So 2,200 microcoulombs per volt. That's what they really want you to say. Okay, essentially. Okay. This is from a GCSE text, I think, actually. I only put this in just to show that when you're charging and discharging capacitors, you can use resistors. I think in the real world, when you're charging a capacitor, generally, pretty much every case, you wouldn't have a resistor in there. And most capacitors are used for their discharge properties. I think I'm right in saying. But the reason why we put resistors in the charging circuits at A level is so that you can study the rise of various things like voltage, because they would just rise instantly to the peak voltage if you didn't have a resistor in there. So they're kind of complicating a system really with charging. And charging is a bit like dielectrics. It got brought back in 2015, I believe, and in the previous specification it wasn't in there. It was maybe in specifications past before that, I'm not sure. And the reason I put this slide in is that when you've got a resistor with a capacitor and a battery in a circuit, then it's a potential divider. So there is a link to that. Okay, even though some students struggle with seeing that those two circuits there are potential dividers, but they are just a battery or a cell. in series with a capacitor and a resistor. So in the charging circuit, when you connect the voltage across the resistor, all of the voltage initially, and the capacitor, all of the voltage is initially across the resistor. But after a certain amount of time, then the charger will charge exponentially, and all the voltage will eventually be across the capacitor. Okay, but it's worth flagging up about the potential divider link there. Now, charging capacitance, there's a bit of a sort of pictorial diagram there about showing the charges building up on the plates. And the rate of flow of charge falls exponentially. And a typical explanation of why that falls exponentially is because as time goes on, the electrons find it more difficult to go to the negative plate because there's more and more electrons on there. So there's electrostatic repulsion. But from looking in past papers quite a lot on AQA, they don't really want that mentioned. Okay, in terms of that kind of thing. What they want is what's written down below there. So when charging a capacitor, you have a series resistor in place in A-level questions. And as the voltage increases across the capacitor, potential divider circuit, and the share of the voltage across the resistor drops and I decreases. I prefer the explanation about electrostatic repulsion, but there we go. That's what's written in the mark schemes. We'll have a good look at the graphs, so we'll just gloss over that graph for now and come back to it when we look at more detail of the graph. And in terms of analogies, you could, because these things are quite difficult to visualize, charging of capacitor could be thought of as analogous to inflating a tire with a pump, the tire size being the capacitance, pump pressure being the voltage applied, and then the airflow rate being the current, essentially, as if that helps some understanding of that. There's some good FET simulations again for capacitors, but you have to enable some of the non-HTML simulations. So I think at the moment, 2024, FET haven't fully changed all of their little simulations over to from Java to HTML. So you might have to run the emulator, I think. Particularly one of those capacitance ones is really good, and you can't run it in HTML5 at the moment. So this is just a repeat of that there. Okay, that slide about capacitance. So capacitance is charge per unit voltage. So measured in farads, coulombs per volt, really. So this was introduced, or reintroduced, sorry, because it was in courses before dielectrics. Okay, so permittivity, which you would have come across if you looked at electric fields. Permittivity, a measure of how difficult it is to generate an electric field in a material. Relative permittivity, the ratio of the permittivity of the material to the permittivity of free space, which appears in the force and field strength equations and potential equations in electric fields. Relative permittivity is called the dielectric constant quite often. It's worth noting. And there's a model that needs to be applied when we're thinking about what's going on with dielectrics. So dielectrics generally are made up of lots of polar molecules. You could think of them a bit like rugby balls there with a positive and negative end. When no charge is stored by the capacitor, there's no electric field, so they're all pointing in random directions. So on the next slide, then, you can see that when a charge is applied to the capacitor, the electric field is generated and the polar molecules move such that they oppose the electric field there, okay? So that the positive is attracted to the negative plate and the negative attracted to the positive plate. So that reduces the overall electric field, which reduces the voltage needed to charge the capacitor, and so that can increase the capacitance of a capacitor, which is an important thing. Capacitors that you buy in electronics shops, then they will have dielectrics in them to have large, to increase the capacitance. And they'll probably have like a Swiss roll arrangement. Usually there could be cylindrical capacitors. It could be a button capacitor as well. And this is another equation, which, as I say, was reintroduced in 2015. There hasn't been many questions on this equation. There have been one or two. So capacitance is equal to the area. And let's need to be specific here, just in case they ever query this. The area of overlap of the plates. Now, the assumption is that the plates are one on top of the other directly. But you could, when there was a question came up a few years ago where it was a variable capacitor and the area changed, the area of overlapped that's how they work. And so it's worth showing students a variable capacitor, the component, what it looks like, an old one, you know, big one you can show and pass around. They've only asked that once, I think, in the AQA course, and fairly recently. Then you've got those two permittivity values there, and then divided by the distance between the plates, d. Now, the relative permittivity of air and vacuum is 1, and students need to be aware of that. They're not exactly the same. I think they differ in something like the 5th decimal place, but you know, to all intents and purposes for A level, we say they're the same. Now, the energy stored is going to result in 3 equations, this section. Okay, so if we consider the capacitor being charged up, and if we consider a change in charge from Q to Q plus delta Q, you can work out that the work done is represented by the area under the graph of voltage against charge, and it comes out to be half base times height because of the triangle, so half QV. Now, there's been lots of discussion over the years about this, about why it's half QV. I'm not going to talk about it in depth there, but there's a link there that talks one version of what's happened to half the energy, because it's worth flagging up to students that in every other part of the course, work done or energy is equal to QV, but it's half QV there. But I'm not going to, I could speak for or talk for a long time about various arguments about what's happened there to the energy, why it's half QV and not QV, but I'm just going to leave it there and you can look that up yourself. Okay. So that's the equation, the initial equation, but there are 2 other variants of that equation that if you substitute in the first equation that we did, Q equals CV or C equals Q over V, then you can get 2 other equations. So that's what we're doing here. Okay. So you've got half QV, you've got half CV squared, and then you get half Q squared over C. I think, on the balance, I think the most common equation to use for energy is the half CV squared. But, you know, you can use any of them. And, well, you can't use any of them. You've got to be careful which ones you use in a question, because more than one variable might change, especially in the toughest questions. There was a really difficult multiple choice asked a few years ago where 2 variables changed, and that caught out loads of students. I think only 13% of students got that right, and that was a multiple choice, so that's a really low, probably the lowest facility of how many people got that right that I've ever seen, in fact. Okay, so yeah, you've got to be careful in the choice of the equation that you're looking at there. Okay, you only really want to deal with something where one of the variables is changing. So capacitor discharge was the thing that people always taught, and so we'll start off with discharge. So you've got the circuit there where if you flick that switch there, the 2-way switch first to the left, and that capacitor C will charge instantly, so we're saying it's already charged. And then we flick the switch to the right, and the capacitor discharges across the resistor. And now that will be an exponential decay, and it will follow the form of those equations there, those exponential equations for charge, voltage, and current. They're all exactly the same. They're all the same. They're all the same equation format, and they're all the same properties of the curves. Okay, for discharging. Now, just you've got to be careful if you do some of the other exam boards. Some of the other exam boards they do vary what they say about I, but the current, in terms of which quadrant they plot the graph in. But I'm not going to talk about that now because I'm talking really about AQA, okay? Right, so if we look at the graphs there, whether it's charge, current, or voltage, they're going to go down exponentially, okay? Now, only one of those is given to you in the exam, in the AQA formula booklet. I think it's Q, I think. And so you just got to be careful. You remember that the other ones are all there as well, okay? If you think about it, you can substitute for Q by using the capacitance and the voltage, and then the capacitance will cancel and so on. And the same there, you can go from the voltage to the current by using V equals IR, and then the R's would cancel either side of the equation. Okay, so you can see where they can all be connected. They're all the same. It's a bit more complicated, only slightly more complicated when you look at charging. So they're, the charge at a given moment is equal to the peak charge multiplied by the exponential function there, and in the index you've got minus t over RC, and RC is what they call the time constant, and it's the same thing then for the voltage at a given time and the current. So the subscript naught stands for peak, really, or starting value. So the time constant comes up all the time in questions, and it's equal to the product R times C. You might wonder why it's called the time constant, but it's explained later on in the PowerPoint. It's the time taken for the capacitor to discharge to 37%, or roughly 37%, of its initial value. And it's also the same time taken for the current and the voltage to fall to 37% of their initial values. And I'll explain where the 37% comes from now in a second. So you can, this is sort of reminds students of radioactivity back at GCSE, similar kind of graph, but it's not half-life. You know, you're going down to 37% and across to the and down, and that value there on the x-axis is the time constant. So I'm just going to skip that slide, come back to it. So why is RC called the time constant? Well, if you think about what it is, R times C, well, R is resistance, C is capacitance. We know two equations. You already know, hopefully, that R is V over I, and capacitance is Q over V. If you substitute in for those variables, you get the time constant to be QV divided by IV, and you've got a common variable there in the fraction of V, so they cancel, so you get Q divided by I, and Q divided by I is, of course, T. Okay, and T is measured in seconds, so time constant. So the units of the time constant are seconds. Okay, and that's always nice to explain where that comes from. And why is it 0.37? Well, if we start off with the charge equation there, so the charge at a given time is the peak charge times the exponential function. So when the time equals the time constant in the index there, you're going to have RC over RC. So what happens then with the rest of that? So you get minus RC over RC in the index, so e to the minus 1. And what is e to the minus 1? Well, e to the minus 1 is 0.37, or 3679. So that's where that comes from, because it's the ratio of the charge now to the initial charge. So that's a neat explanation of that. Now, if I go back a few slides, there's an equivalent for charging. We'll have to talk about charging separately in a bit. In charging, the time constant is the time taken to go to 0.63% of the final voltage in this case, I suppose, for the charge there, or the final, for that graph, or the final charge. But for charging, you can see that the current and the voltage graphs are different, okay? But I'll come on to that now later. Just wanted to show you that the time constant for charging is 0.63 times the peak voltage, or the peak charge. And 0.63, of course, sorry, I should have said that. 0.63 is 1 minus 0.37, okay, and that's where that comes from, really. Right. So uses, there's just another slide on uses there. Worth remembering, one use for students that they can remember back at power supplies is always a good one. And they could be used to cause a time delay. So in those, I can remember, I used to have an old camera quite a few years ago now, and you pressed a button on the camera, and then it had a time delay of 5 seconds, I think, and then it would take a photograph, so that the person who was taking the photograph could be in the photo. And so this little slide here, this is actually from a GCSE book from years ago when it was an extension topic at GCSE capacitors. Shows you how much courses have changed in UK schools over the years, because this is a year 13 topic now. But you could see there the potential divider kind of set up there, and you can see that, well, you can have a read of that and see what's happening. So that's a nice use of the capacitor that can be understood fairly straightforwardly. Now, charging, as I said, got introduced. I don't think I'd ever taught it prior to that. So charging was introduced in 2015 in the AQA course. Now, two of the graphs look the same, and the current one looks different. Okay, so the current one there is exactly the same as it was for charging for the AQA course. For discharging for the AQA course. Now, I think I'm right in thinking that would be reflected in the X, and it would look like this down in this quadrant in OCR, because it changes direction is the argument, okay? But anyway, for AQA, we say that we just talk about the size of the current, and it goes down exponentially. but the voltage and the charge for charging clearly rise. Okay, and we need to come up with a look at the maths behind that as well. And it says there that the charge is the area underneath that graph, the IT graph. So in terms of charging, if you just put a battery around a capacitor, then it will charge instantly. So you have to put a resistor in there to get this kind of graph. Okay, and we'll have a little look into that. So the equations here, the voltage and the charge graph look the same, and they're a 1 minus exponential graph. So those equations, well, one of those equations is given to you in the formula booklet. I think it's the Q1, I think. Just got to remember that the current, though, is still just a standard exponential decay, not a 1 minus exponential. Now, you don't have to know where in the maths behind where that comes from, the rise, than the 1 minus the exponential, but there is a slide towards the end, I think, that explains it, if you'd like to know, but it's beyond the scope of the course. There is such a thing as half-life as well. This used to come up in older AQA questions. Not sure if it's come up much recently, but it's still worth teaching about. So there is a half-life of a capacitor discharge. So the time taken for the charge or the voltage to decrease to half the initial value. And this is actually 0.69 as opposed to 0.37, like we saw before. But it's actually 0.69 times RC as opposed to 0.37 times the voltage. So let's have a look at what that means. Where does that come from? So if you start off with the voltage equation, V equals V naught with the exponential there, if we look about the half-life, then we're looking to go down to half the peak value. So you can substitute for V as half V naught, and then you can simplify the equation. There's a few steps being done there, and then taking logs, and you get so you've cancelled the V naughts on either side there, so you get half equals e to the minus t over RC. Then you take logs, and you get that expression there, and then you rearrange that and take logs of the log of a half, and you get that. That's where that 0.69 comes from. Now, one fact that's useful to remember as well, perhaps, is that after about 5 lots of the time constant, the capacitor will have pretty much discharged or fully charged. It's a useful thing to remember. So the half-life doesn't come up that often these days, but it could do. I think it is still in the specification. So, but it's easy to confuse, I think. The 0.67 of the peak voltage or charge for charging, and the 0.37 of the peak voltage or charge for discharging, and then you've got 0.69. So students need to get clear in their mind where the numbers come from, and they could always use their calculator if they really understand this to work these things out. Now, it's worth talking here again. The examiners, when they set questions, I think they assume everyone understands the jargon that's been used over the years. And one thing worth mentioning is for capacitors, or this topic, is full-scale deflection. And it's important in magnetic fields, induction, for instance. But I usually mention it here. So full-scale deflection, examiners assume that students understand what that term means. So for those that haven't come across that before, it means the maximum thing that can be read off a analog meter. So in the case of that voltmeter there, 500, whatever the units are, maybe they're volts, 500 volts, and then the center reading analog machine there, ammeter on the bottom right, the maximum thing you could read there would be 50 microamps. So that's the full scale deflection. Okay. And sometimes they ask questions saying, why would you use an analog meter? And analog meters are good for fast changing AC signals, I'd say, really. So the center reading one there, if you've got a fast changing AC signal, if you had one of the standard multimeters, digital multimeter, you just see a cycling of numbers, and you probably couldn't say what the peak value was. Whereas with an analog, you can see how far it's moving, the maximum deflection. So yeah, that's an answer that could be used for that. When you do the CPAC experiment for this, then they ask you to do a log graph of one of the discharging data sets, And this slide here is just covering how you start off with a V equation and you get a y equals mx plus c by using taking logs and rearranging the equation. So you should get a straight line. And the gradient of the straight line is -1 over the time constant. So that's a good thing to check. Because the point of the CPAC really is confirming that the time constant, the product of the resistance times the capacitance, is equal to what you can work out in the experiment using the graphs. You can have exponential graphs, and in this case, usually for my classes, I ask the class to take one of the discharge data sets and then take logs and plot log of the voltage against time, and then you get this graph, and hopefully can confirm that it's pretty close so that the tolerance isn't too high. With regard to the CPAC experiment, it can last a few lessons, to be honest, but I used to get students to do about 16 graphs at one point, but I've reduced it a little bit now to sort of a couple of variations of charging and discharging, and the students get the hang of that. One year I did get students to do it using data loggers because I thought that would be useful, but I think I overestimated students' skills with Excel and trimming the data because they ended up having huge data sets, and that ended up being more hassle than it was worth for me. Maybe I should have thought about it a little bit beforehand, but no, I think it's better to use the stopwatch and a multimeter, to be honest, for that experiment, having learned through experience. And this slide is beyond the course. It's just talking about the derivation of the exponential equations. I know often I ask students when I talk about exponential decay, what does an exponential mean? And most students are not able to say what it means. And to me, an exponential decay happens when the rate of change of the variable, so in this case q, the rate of change of the variable is proportional to the variable itself. And that to me is the definition of an exponential decay. But that's beyond the course, but just for those that are interested in that. And then there is a derivation there of the charging equations, the 1 minus the exponential equations there. But it's just an extension. So these last couple of slides are just extended work, really. And I think this is possibly the last slide. Now, I think it's still acceptable in some mark schemes, depending on the question, obviously. But if you have to work out the time constant in a question, you are still, I believe, allowed to use this little trick. Well, I mean, it's not a trick, it's a real thing that you could use, but it's one of those things that used to be more common a long time ago in mark schemes. So if you wanted to work out the time constant, you could take a tangent from the peak value of the voltage or the charge and go down to the x-axis, and where it cuts the x-axis, that is the time constant. And there's a little proof of it there on in the text below. But generally that wouldn't be the way of getting the time constant that the examiners wanted you to use. So I'd hesitate to advise that as the first thing. And quite often you might not be able to use that. You might not be given enough information to do it. But it's just a neat little thing to show students, I think. A use of capacitors, which students have all used, I imagine, mobile phones, tablets, cash machines. Quite a lot of them would use capacitive displays. And so this is a little figure, a little bit of information about capacitive displays and how they work, to show that capacitors are really really fundamental to everyday life, really, in terms of electronic stuff. Now, in terms of the exams or the topic, I think students find capacitors generally the theory okay. Students who don't do A-level maths might struggle a little bit, but need a bit of preparation. There's a good section in the Advanced Physics for You on maths for physics. I'd recommend that section in Johnson's Advanced Physics for You. There's a really good section there for those who don't do A-level maths and understanding natural logarithms and things like that, and exponentials. So, there could be a struggle if that's not dealt with or brought in a little bit earlier. So if you've got students that don't do A-level maths, it's worth priming them beforehand a little bit on the maths that's needed, because it'll come into play as well for radioactivity as well. But I think, especially for the AQA course, that it's the questions that can be quite hard. Some of the hardest questions that I've seen the AQA exam board produce over the last 10 years have been on capacitors. So whilst the theory, I think, is okay for most students to understand, I think the questions can be quite stretching. Always worth bearing in mind. Okay, so that's 30 minutes. I think that's enough. So I hope you enjoyed that. Bye for now.